A rectangular coil carrying current is suspended in a magnetic field. A rectangular coil carrying current suspended in a magnetic field. Here, the magnetic field is indicated by horizontal parallel arrows. A uniform magnetic field is taken. Inside this uniform magnetic field, a coil PQRS is placed. A rectangular coil PQRS is placed. The current is flowing along the direction PQRS. In the branch PQ, the current is flowing down. In the branch RS, the current is flowing up. The length of this coil PQ is equal to L. The breadth of the coil QR is equal to B. Now, when the current is flowing, we can consider a current carrying conductor placed in a magnetic field. So each branch PQ can be considered to be one branch, a conductor, and QR another conductor placed in magnetic field, RS another branch of conductor placed in magnetic field. Like this, we imagine different parts. In QR and PQ, in QR the current is flowing in the direction of the magnetic field. In PS the current is flowing opposite to the direction of magnetic field. In QR the current is in the direction of magnetic field. In SP the current is opposite to the direction of magnetic field. So these two coils will not experience any force. These two branches will not experience any force because the force is 0 if the angle theta is 0 or theta is 180. So in QR the angle theta is 0, in SP the angle is 180 degrees, hence the force acting on them is 0. PQ and RS both are perpendicular to the magnetic field, so they experience maximum force. PQ, RS are placed perpendicular to the magnetic field, so they experience maximum force. The force on PQ is given by BIL. Similarly, the force on SR is also equal to BIL. By applying Fleming's left-hand rule, we notice that the force on PQ is outwards, out of the screen, and the force on RS is into the screen. The force on PQ is out of the screen and the force on RS is into the screen. So these two forces constitute a couple. So a torque acts on the coil when a current passes through this coil. So whenever a rectangular coil carrying current is placed in a magnetic field, it experiences a torque. Expression for torque. Here two forces are acting, each of magnitude BIL. They are acting in opposite directions. Moreover, they are acting at different points of the coil. Hence, they constitute a couple. The forces acting on this coil, they constitute a couple. The moment of the couple is defined as one of the forces multiplied by perpendicular distance. The torque due to the couple is defined as one of the forces multiplied by perpendicular distance. The perpendicular distance between the two forces is the breadth of the coil B. So the torque acting on this coil is BIL into small b, capital BIL into small b. That is equal to BIA, where A is area of the coil, surface area of the coil. LB is surface area of the coil. So the torque becomes equal to BIA. This is the torque on one turn. If there are n turns of the coil, then the total torque acting on the coil is equal to BIAN. The total torque acting on the coil is equal to BIAN. This torque is called as deflecting torque. Because of this torque, the coil will be deflected from the plane of the magnetic field. Due to this torque, the coil will be rotated. The PQ side moves up and the RS side moves down. If the coil is held such that the plane of the coil is making an angle theta with the magnetic field, then the component of induction B cos theta will be responsible for the torque. Hence, the torque tau is equal to BIAN cos theta. This relation is valid for a plain coil of any shape. It need not be a rectangular coil. This relation is useful and it can be applied for any coil of any shape. Moving coil galvanometer, MCG. It works on the principle of torque acting on a rectangular coil carrying current placed in a magnetic field. MCG, moving coil galvanometer, works on the principle of torque acting on a current carrying rectangular coil placed in a magnetic field. First, let us analyze the setup. Two powerful pole pieces, NS, represent the north and south poles of a horseshoe magnet. Their shape is concave. So, concave shaped poles are there for the horseshoe magnet. In between the two pole pieces, there is a circle represents the head of a soft iron cylinder. A soft iron cylinder is placed in between the two concave shaped poles of horseshoe magnet. On the circle, you notice lines which represent the rectangular coil. This rectangular coil is connected by a suspension wire which is made of phosphor branch. At the phosphor at a small height above this pole pieces, you notice mirror. A small mirror is mounted on this phosphor branch wire. The bottom end of this phosphor branch wire is connected to a restoring spring. It is connected to a spring at the bottom. So this is the cross-sectional view of this moving coil galvanometer. Moving coil galvanometer. The purpose of soft iron piece is to increase the magnetic field. The magnetic field inside the coil will be increased due to the presence of soft iron cylinder. The concave shape of the pole pieces, it provides radial magnetic field. Inside the radial magnetic field, the coil will be always parallel. The surface of the coil will be always parallel to the magnetic field. That is why the poles are concave in shape. Phosphor branch has high Young's modulus and low rigidity modulus. So twisting becomes easy. Due to the torque, the phosphor branch wire will be twisted. High Young's modulus, it prevents elongation of the wire. So it will hold the cylinder and the coil very easily because its Young's modulus is very high. This is the purpose of the phosphor branch wire. Relation for measuring the current with moving coil galvanometer. Let us derive a relation for measuring the current with moving coil galvanometer. When a current I flows through this coil, through the suspension wire and through the coil, a couple acts on the coil due to the magnetic field of the horseshoe magnet. This couple is known as deflecting couple. And the magnitude of this couple is already derived. It is given by tau is equal to BIAN, where B represents the magnetic field induction, I is the current flowing in the coil, A is area of the coil, and N the number of turns in the coil. B is magnetic field induction, I current, A area of cross section of the coil, N the number of turns of the coil. As the coil rotates, along with it twists the suspension wire. Phosphor branch suspension wire will be twisted by the rotation of this coil. Hence, a torque sets in due to the rigidity elasticity nature of the suspension wire. Due to its rigidity modulus, because of the suspension wire rigidity, another torque sets in which tries to bring the coil to its natural state. So it is called as restoring torque. A torque will be developed in the suspension wire which tries to restore the coil to its original direction. So we call this as restoring couple. If C is the couple per unit twist of the suspension wire, for twisting say by 1 radian, the couple is say C. For deflecting through an angle theta, after deflecting the wire through an angle theta, the restoring couple produced becomes equal to C theta. For unit angle, the couple required is C. For a deflection theta, the couple will be C theta. The coil comes to rest after deflecting through an angle theta, provided the deflecting couple and the restoring couple become equal. When the restoring couple becomes equal to the deflecting couple, then the coil comes to the equilibrium state. So the coil rotates by an angle theta and then stops when these two couples become equal. So when equilibrium state is attained, the two torques are equal. Therefore, BIAN is equal to C theta. BIAN is equal to C theta. Therefore, I is equal to C theta by BAN. Therefore, I is equal to C theta by BAN. So, I is equal to K theta, where K is given by C by BAN, which is a constant for a galvanometer. So, the current with moving coil galvanometer is measured with the relation I is equal to K theta. Measurement of current by moving coil galvanometer. The relation for current in moving coil galvanometer is I is equal to C theta by BAN, that is equal to K theta, where K is a constant of the galvanometer given by C by BAN. So the value of K depends on C, couple per unit twist, B, the magnetic field induction, A, the area of the coil, and N, the number of turns of the coil. So all these are constants. So K is a constant. K value will be calculated by taking the values of C, B, A, N. Then theta will be measured by using lamp and scale arrangement. Theta is measured using lamp and scale arrangement. So I is calculated using the values of K and theta. So from the relation I is equal to K theta, by calculating K and theta, we calculate I. This is a very sensitive galvanometer. Moving coil galvanometer is very sensitive. That means it can measure very very low values of currents, very small currents of the order of nanoamperes. It can measure currents of 10 to the power of minus amperes, that is nanoamperes, very small currents. That's why it is called a sensitive galvanometer, sensitive device. Comparison of moving coil galvanometer and tangent galvanometer. Comparison of moving coil galvanometer and tangent galvanometer. In moving coil galvanometer, the coil moves, whereas in tangent galvanometer, the magnet moves. So it is a moving coil type. MCG is moving coil type and tangent galvanometer is moving magnet type galvanometer. The moving coil galvanometer can be kept in any direction. The coil in the moving coil galvanometer can be kept in any direction. But in tangent galvanometer, the coil should always be kept along the magnetic meridian. It should be kept only along the magnetic meridian. It should not be kept in all directions. That is in tangent galvanometer. The current through the coil is directly proportional to the deflection in moving coil galvanometer. In moving coil galvanometer, the current is directly proportional to deflection. But in tangent galvanometer, the current is measured by the relation I is equal to k tan theta, so it depends on tan theta. So it is not directly proportional to theta, but it's proportional to directly tan theta. That is in tangent galvanometer. Moving coil galvanometer is accurate. Its measurements are accurate and it can measure up to 10 to the power of minus 9 amperes of current, very low currents. Moving tangent galvanometer is not so accurate because the measurement of I depends on tan theta. The measurement of current in tangent galvanometer depends on tan theta, hence it is not so accurate. The value of current or the constant in moving coil galvanometer doesn't depend on Earth's magnetic field induction. The constant in moving coil galvanometer doesn't depend on Earth's magnetic field induction, whereas in tangent galvanometer the constant depends on horizontal component of Earth's magnetic field induction. Horizontal component of Earth's magnetic field induction, it plays a role in the constant of tangent galvanometer. So its value varies from place to place, whereas the constant in moving coil galvanometer is the same at all places. Stray magnetic fields have no effect on moving coil galvanometer because there is a strong Harshaw magnet in moving coil galvanometer. External magnetic fields have no effect. In tangent galvanometer, a weak magnetic field, Earth's magnetic field is very weak. So if there are surrounding high magnetic fields, they can influence the deflection in tangent galvanometer. That's why we say external magnetic fields can influence the readings of tangent galvanometer, but not in moving coil galvanometer. These are the differences of moving coil galvanometer and tangent galvanometer. Moving coil galvanometers will be converted as table galvanometer, in which there will be a scale. A pointer will be moving on the scale. To obtain full deflection on this scale, some current is to be passed. That current is known as full scale deflection current. That is indicated by Ig. So Ig is known as full scale deflection current of the galvanometer. Generally, a galvanometer will be indicated with an arrow mark in a circle with a series resistance. So it will have some resistance that is indicated with G. G indicates, capital G indicates the resistance of the galvanometer and Ig indicates the full scale deflection current. If larger currents than Ig are passed through this galvanometer, it gets spoiled. So to protect it from high currents, we connect a low resistance, a small resistance parallel to the galvanometer, and we call this such a device as shunt resistance. And the principle of connecting a small resistance in order to protect the galvanometer is known as shunt principle. Suppose S is the shunt resistance. It is connected across the galvanometer. If I is the circuit current, total current from the circuit, a part of the current passes through the shunt. A majority of the current passes through the shunt. Let us indicate the current through the shunt as Is and current through the galvanometer as Ig. The full scale deflection current through the galvanometer is Ig and the remaining current will pass through the shunt, that is Is. Then I is branched off into two parts, Ig and Is. So applying Kirchhoff's first law, we get I is equal to Ig plus Is. I is equal to Ig plus Is. Moreover, since the resistance, shunt resistance S and the galvanometer resistance G are parallel across the ends AB, the potential difference across these two must be equal. From Ohm's law, we know that potential difference is equal to current into resistance. So the potential difference between AB across the galvanometer is Ig into G. The potential difference across the galvanometer is Ig into G. The potential difference across the shunt resistance is Is into S. Is into S is the potential difference across the shunt and Ig into G is the potential difference across the galvanometer. These two are equal because they are parallel. Since S is very small compared to G, therefore Ig is very small compared to Is. So a large current passes through the shunt and only a small current will be used for measuring the current. This is the advantage of a shunt resistance. Derivation of the shunt principle. Let us derive a relation for finding the required shunt resistance. It depends on the current that is to be measured for full scale deflection. To measure larger currents, we require shunt resistance. To calculate the shunt resistance, our aim is to calculate the shunt resistance, yes. The relation between the currents is taken as I is equal to Ig plus Is. And the relation between potential differences between A and B is Ig into G is equal to Is into S. Ig into G is equal to Is into S. From this relation, we will get S is equal to Ig into G divided by Is. Ig into G divided by Is. From equation 1, we can write it as Is is equal to I minus Ig. From equation 1, we can write Is is equal to I minus Ig. Substituting the value of Is, we get S is equal to G by Ig divided by I minus Ig. S is equal to G into Ig by I minus Ig. Let us bring Ig into the denominator. Therefore, we can write S is equal to G divided by I by Ig minus Ig by Ig. Bringing Ig to the denominator, we will write S is equal to G divided by I by Ig minus Ig by Ig. Let us indicate I by Ig with N. Therefore, S becomes equal to G divided by N minus 1. S is equal to G divided by N minus 1. Ig by G is the fractional current that passes through the galvanometer. So, I by Ig is the number of times the higher the circuit current is to the galvanometer current. So, nth part of the current will pass through the galvanometer. If we indicate I by Ig is equal to n, that means only 1 by nth part of the current will pass through the galvanometer. And the principle of shunt becomes equal to S is equal to G by n minus 1. Generally, this principle is called as shunt principle. This relation S is equal to G by n minus 1 will be called as shunt principle. Ammeter. Ammeter is a device used for measuring the current. In fact, moving coil galvanometer also can measure very small currents. So it can also be called as an ammeter. But it cannot be used in a circuit for measuring large currents. For measuring large currents, we use a galvanometer with a shunted galvanometer called as ammeter. A galvanometer with a shunt is called as ammeter, and it is used for measuring large currents. For measuring a current, an ammeter should be connected in series with the circuit. Ammeter should be connected in series with the circuit. A small portion of the current passes through the galvanometer and a large current passes through the shunt resistance. A large part of the current is bypassed by the shunt resistance, and a small part of current will be used for measuring the circuit current. Because of this galvanometer resistance, the circuit resistance will increase by a small amount. Hence, the circuit current decreases. So, the resistance of ammeter should be as small as possible so that it may not affect the circuit current. For an ideal ammeter, the resistance should be 0. For an ideal ammeter, the resistance should be 0. We call an ideal ammeter is one whose resistance is 0. But in practice, such ammeters do not arise. Voltmeter. Voltmeter is a device used for measuring the potential difference between 2 points. Voltmeter is a device used for measuring the potential difference between 2 points in a circuit. A voltmeter can be constructed by using a galvanometer. A voltmeter can be constructed by connecting a high resistance in series with a galvanometer. If a high resistance is connected in series with a galvanometer, moving coil galvanometer, it can act as a voltmeter. In a circuit, a voltmeter will be connected parallel to the circuit element. To measure the potential difference, voltmeter will be connected parallel to the circuit between 2 points. A small current from the circuit will flow through this voltmeter. A small current from the circuit flows through the voltmeter, and thereby we measure the potential difference. By connecting a voltmeter across an element, because of the connection of voltmeter across a device element, the resistance of the circuit decreases by a small amount. The circuit element resistance decreases, hence the circuit current increases slightly. There is a slight increase in the circuit current whenever we connect a voltmeter. The effect of the voltmeter will be small provided its resistance is very large. So voltmeter should be devised such that its resistance is as high as possible. Voltmeters must have very high resistance. A voltmeter with infinite resistance is called as ideal voltmeter. That means which cannot affect the circuit current. An ideal voltmeter is one which doesn't affect the circuit current. For an ideal voltmeter, the resistance should be infinity. So far we have discussed how a voltmeter can be constructed and how it will be connected in a circuit. Now we will pass on to the mathematical calculation of the resistance that is to be used in a voltmeter. If R represents the external resistance that is to be connected in series with the galvanometer, then the total resistance becomes G plus R, G being the resistance of the galvanometer. The total resistance of the device becomes G plus R. The full scale deflection current of the galvanometer is Ig. So it is equal to a potential difference V given by Ig into G plus R. This relation is obtained from Ohm's law. Ig is full scale deflection current and the total resistance of the device is G plus R. So the maximum voltage that it can measure is given by V is equal to Ig into G plus R. Therefore, V by Ig is equal to G plus R. Therefore, R is equal to V by Ig minus G. So, in order to calculate the resistance required to convert a galvanometer into a voltmeter, we can use this relation R is equal to V by Ig minus G. V is the desired voltage and Ig is full scale deflection current. G is galvanometer resistance. R is the series resistance required. So we can devise a voltmeter of required range. Using the value of range, we calculate the resistance needed to be connected in series with the galvanometer. So this relation R is equal to V by Ig minus G gives the calculation of resistance needed. Summary of this class. A rectangular coil carrying current, if placed in a magnetic field, it experiences a torque. The torque is given by tau is equal to BIAN cos theta. This principle is used in the moving coil galvanometer. The relation that is used for measuring the current in moving coil galvanometer is I is equal to C theta by BAN, that is equal to K theta. This is a very sensitive galvanometer and measures the currents accurately than tangent galvanometer. A small resistance connected in parallel to it is called shunt. Using shunt, we can measure large currents with moving coil galvanometer and call it as an ammeter. The relation for shunt is